Hey class, we have one more topic on orthogonality to discuss before we move on a new chapter of determinants starting tomorrow. Today we'll talk about orthonormal bases, why they are important, and how to find such bases for a given vector space. And then the connection between matrices and a basis for a vector space is that we can always realize a vector space as the column space of a matrix by taking bases vectors and putting them as columns of a matrix. So we'll see what kind of properties orthogonal matrices have and how to exploit them, how to use them to simplify some of our work. Now, let's start with what is an orthonormal basis. So here is the definition. I'm going to say it like this. A basis of vectors q1, q2, qn for some vector space V, for example, is orthonormal if there are two conditions now that need to be satisfied: the ortho part and the normal part. So condition number one is if these vectors are mutually orthogonal. So if the vectors are mutually orthogonal. Mutually here means any two vectors are orthogonal. That's what it means. And the normal part, each vector has length 1. Okay, so normal vectors are considered the vectors of length 1. Orthonormal, these are vectors of length 1, and they are mutually orthogonal. Now, both of these conditions can be written in the following way. So the same conditions here with exactly one equation, which says that Qi transpose Qj is 0 if I is different from j, right? So what does that mean? It means if you actually take two different vectors, say q1 and q5, when you take their dot product, you get 0 because the two vectors are orthogonal, and you get 1 if I is j. So that means if you take Qi transpose Qi, you're going to get 1, which says that the vectors are orthogonal, so if are orthonormal. So if we only want orthogonality, then we look at this condition and let this one not be 1, but whatever the length is. And if we want the vectors to be normal, orthonormal, then we want their length to be 1. Now, of course, if you start with a basis for some vector space of vectors which are just orthogonal, mutually orthogonal, but not normal, what you can do is you can divide each vector by its length and get a new basis of vectors, which is normal. Okay. So that's the definition. We will always use this part. All right. Now, let's prove one very important property of orthogonal vectors, and that is that if the vectors are mutually orthogonal, so if the vectors q1, q2, qn are mutually orthogonal, then they are linearly independent. Now you see, this means that orthogonality is a stronger property than independence. So if we have orthogonal vectors, then we know for a fact that these vectors must be linearly independent. How to prove this? Well, let's assume, so the proof will be by contradiction, or it doesn't have to be by contradiction. We can just take a linear combination. So take a linear combination that gives 0. Namely, let's say C1Q1 plus C2Q2 plus CNQN gives us 0. To show that the vectors are linearly independent, we must show that each of these C's is 0. So how are we going to do that? Well, we're going to use orthogonality. We're going to multiply this equation on both sides by Q1 transpose. So I will have Q1 transpose times this entire vector, or this entire linear combination, which is also a vector, I suppose. So this equals Q1 transpose times 0, which is 0, right? Now, as I open parentheses, as I distribute this multiplication, I can factor C1 always out, C2 out, and so on, because these are just numbers, right? It's really the vectors that have to respect the order of multiplication. So what we get is C1 Q1 transpose Q1 plus C2 Q1 transpose Q2 plus Cn Q1 transpose Qn equals 0. Now, by orthogonality, we know that Q1 transpose Q2 is 0 because the two vectors are orthogonal. We also know Q1 Qn, Q1 transpose Qn is also 0. The only thing that isn't 0 is Q1 transpose Q1. So this is not 0. So ultimately, this entire equation boils down to C1 Q1 transpose Q1 is 0, with this not equal to 0. Then from here, we have to have that C1 is 0. Now, similarly, so we know C1 is 0, right? Now, how to show that C2 is 0? The same trick. Multiply by Q2 transpose. You could multiply this part by Q2 transpose, or you could multiply this part by Q2 transpose. It doesn't matter. The only thing that is going to survive will be Q2 transpose Q2. Everything else will be 0 by the orthogonality of the Q's. So that will force C2 to be 0, and so on, Cn to be 0. So I could have written this in a more general way, where instead of taking Q1, I could have taken some Qk, for example, the kth one, and show arbitrarily that the kth one, that Ck would have to be 0, which in turn proves that everything is 0. So this is the proof that if you take a linear, orthonormal vectors, orthogonal vectors, the normal part is not important for linear independence, but if you have a collection of orthogonal vectors, then you have a collection of linearly independent vectors. Remember, we always treat the 0 vector as a linearly dependent vector. Okay. With this, we see that when we take a collection of vectors, we really do have a basis for the span of those vectors. So this vector space V over here that I have really is just span of the Q's, right? Whenever you take a set of linearly independent vectors, you have a basis for the space spanned by those vectors. Okay, now what happens if we put these vectors into a column matrix? Sorry, as the columns of a matrix. So let's take a matrix Q, which has columns Q1, Q2, all the way to Qn. Now, I don't know if this matrix is square because I have no idea how many components these vectors have. What I know is that they should have at least n components, because if they don't, then I would have linear dependence. So the number of columns being n means that the space that they generate or that they span has to be at least n dimensional, so possibly bigger. So I'm going to assume that this matrix is m by n I just know that m must be bigger than or equal to n because these vectors are mutually orthogonal. Otherwise, the pivots have to be at least have to be at least n. Okay, now how to translate this qi transpose qj equals 0 for I different from j and 1 if I equals j. Well, qi transpose qj would mean I should multiply rows by columns, looking at the columns of the matrix. So if I were to look at q transpose q, what would I get? So in Q transpose, I would have Q1 transpose as the first row, Q2 transpose as the second row, Qn transpose as the last row. And then in Q, I have, well, the Q's as columns. Now, what do I get? So obviously, I'm going to get an n by n matrix. So this will be a square matrix. And how I get it is I do first row times first column. So let's just do the standard row by column multiplication. Well, Q1 transpose times Q1 ends up in the first position, in the 1, 1 position, and that equals 1 because Q1 transpose times Q1 is 1, because we have an orthonormal basis. If we take Q1 transpose times Q2, because these vectors are orthogonal, I know that I'm getting 0. And the same is true for all the other vectors, right? Q1 is orthogonal to all of them. Therefore, Q1 transpose times any of those vectors gives me 0. So I know that in the first row, I have 1 and then a bunch of zeros. What happens with the second row? Well, now I have Q2 transpose times Q1. I know that is 0 because the vectors are orthogonal. Then Q2 transpose times Q2 gives me 1. And in fact, you see the pattern. You get the identity matrix. A bunch of zeros. So above, below, right? So no matter whether the matrix Q is square or rectangular, what we get is that Q transpose Q is the identity matrix. Now, pay attention here. This is a very important property. We want to sort of jump in and say, so Q transpose must be the inverse. Well, remember that the rectangular matrices don't have inverses. But if the matrix Q is square, so this is important, if Q is square, then Q transpose equals Q inverse. And only in this case, we call Q an orthogonal matrix. The the columns are orthonormal, but the name is orthogonal, even though arguably maybe it should have been orthonormal, but it's not up to you and I to decide what to call these matrices. It is what it is. The notation is what it is. But the important part that I want you to remember is that only if Q is a square matrix, then we call that matrix an orthogonal matrix. So if I say, okay, let Q be an orthogonal matrix, then you understand that Q is a square matrix. You understand that the inverse of Q is its transpose. And you understand that equivalently, that the columns of that matrix are orthonormal. In fact, in that case, both the columns and the rows would be orthonormal. Let's look at some examples of orthogonal matrices. So I'm just going to write a reminder that a matrix is orthogonal if it is square, and it satisfies the equation Q transpose Q is the identity. If it is not square, it could satisfy the first equation, but we would not call it an orthogonal matrix. Our first example is a rotation in 2 by 2. So what happens is, remember, I've mentioned this many times, when we multiply by a matrix, we transform the vectors that we apply this matrix to. So if you take this Q matrix, which is cosine theta, sine theta, negative sine theta, cosine theta. Why is this matrix an orthogonal matrix? Well, clearly the dot product here between these columns is 0. But also, if you look at the length of the first column or the second column, it would be the same expression. The length would be just cosine squared. Well, the length squared would be cosine squared theta plus sine squared theta, but we know that this is equal to 1. So this is an orthogonal matrix. Its inverse is the transpose. So I don't have to apply Gauss-Jordan to find the inverse. And I will get cosine theta, negative sine theta, cosine theta. What does this matrix do? We're not going to go into linear transformations in this class. I'm not going that fast with the material, but essentially, I want you to understand what this rotation means, because it's especially important for those students who are perhaps in computer science. This is typically what is used on your computer or tablet or phone, whatever, when you have a screen, on how you rotate, how things are rotated, what would happen, or how the software would rotate an image, for example. So what this matrix does is, if you have a vector like that, it would rotate it by theta degrees in the counterclockwise direction. So the new vector would be there, for example, and the difference between the two will be theta. So you would have the same length of the vector. Lengths are going to be preserved, but you will have that rotation. Now this is for one vector, but imagine this matrix does it for all the vectors. So if you multiply any vector in the 2D space, or this matrix by any vector, then you will get its rotated image. And if you apply this on say on an entire picture, what you will get is that picture rotated by theta degrees. You could rotate it by 90 degrees or by a different angle. And then if you want to go back, well, you just have to rotate by negative theta. And to see that that's exactly what you're getting, So it would make sense, right, that the inverse rotation would be a rotation by negative theta. Let me write that. And what you can use as a key property of sines and cosines to get to the inverse rotation without looking at the transpose matrix is the fact that cosine of negative theta is cosine of theta because the cosine is an even function, whereas sine of negative theta is minus sine of theta because the sine is an odd function. So if we were to replace negative theta instead of theta here, so if you wrote cosine of negative theta, you would just get cosine of theta, which is exactly what we have here. But for this expression, you have minus sine of negative theta. This minus could come out front, and the minus times minus is plus. So this is just sine of theta, which is exactly what we have here. Similarly, sine of negative theta is negative sine of theta, and the cosine stays the same. So you see that Q transpose or Q inverse is what you would get if you try to rotate by a negative theta. So some interesting properties. And this is exactly the types of matrices, although when we do computer graphics or when we work in 3D space, we can have the equivalent 3D matrix, but this is for 2D rotation. So anytime you have a picture, this is the matrix that would rotate your image counterclockwise by theta. And then obviously minus theta would give you a clockwise rotation. So this way by negative theta, that would be the inverse rotation. Okay, another example. We already we've seen these matrices. These are permutation matrices. And we showed for permutation matrices that P transpose is the inverse. So these are matrices P that rearrange the order. So permutation matrices P change the order of components of vectors. Right, so for example, if we look at the matrix 0, 0, 1, 1, 0, 0, 0, 1, 0, and we applied it to the vector x, y, z, it will rearrange these components x, y, z into y, z, x. So similarly, again here, you're going to have that the length of the vector is exactly the same thing. So x, y, z, and y, z, x have the same lengths. Things have been rearranged. And the permutation matrix is obviously orthonormal because the lengths of each column is 1, whereas the two by two columns, they're mutually orthogonal. So orthogonality is another way to prove that that permutation matrices satisfy P transpose P is the identity. We have reflection matrices. Now, these matrices are of the form Q equals identity minus 2 times U transpose, where this vector, so U is a column vector that satisfies U transpose is 1. So this is a unit vector. Any unit vector would give you an orthogonal matrix. So if you just wanted to design an orthogonal matrix, take any unit vector in R3, for example, and you would get a reflection. Now, I don't have to take them in R3, I could take them anywhere, but the idea of what happens is So just to show this geometrically, you would have, let's say, some vector. You're treating, so a reflection is, imagine you have a mirror, and now you have a vector here, right? So how do you reflect? Well, you treat this dashed line as a mirror, and you reflect about it to get this vector. And so this is what you would do, what you would call a reflection in geometry. But the nice thing about it, and what we're trying to explain here in linear algebra, is that we can actually take this vector and represent this whole action of reflecting as a matrix multiplication by some orthogonal matrix Q that has a form such as this one. So how could you construct one? We'll just take literally any U that is of unit length. So a specific example could be U equal to, well, if I want any vector, for example, 1, 1, 1, the problem is that this vector, U transpose U for this vector is 3. And I would like it to be 1, so I better divide by the length of this vector. The length of this vector is root 3, so if I just do 1 over root 3, then I'm going to get a unit vector. So you see, literally any vector that is not the 0 vector can be made into a unit vector by simply dividing by its length. So then what the matrix U transpose would look like from here, well, I will have a root 3 from U and a root 3 from U transpose, which I can factor out. So I will have a third times some big matrix, which literally is a matrix of 1s. This is a rank 1 matrix. And no matter whether you're in R3 or you're in R5 or whatever R space you want to take, U transpose is always a rank 1 matrix. So it will have a bunch of numbers inside, but the rank of the matrix will always be 1. If you want to construct a rank 1 matrix, this is it. Take any U dot that is not 0, then U times U transpose will give you a rank 1 matrix. Okay, so we have this matrix, then Q, and you can test this for homework that Q really satisfies the condition if you want to multiply. So we would have the identity minus 2 of this. So you have 1, 1, 1 minus 2 times U transpose, which is 2/3, times 1, 1, 1, 1, 1, 1, 1, 1, 1. And when you take that difference, it's really along the diagonal where you have to pay the most attention. 1 minus 2/3 would be a third. So I have a third along the diagonal. And then I have negative 2/3 everywhere else. All right. And because this matrix Q is symmetric, in fact, what we have is that the matrix is its own inverse. Q transpose equals Q, therefore Q is Q inverse. So try multiplying this matrix by itself and seeing what you get. Now, I made comments on with these examples that when you have an orthogonal matrix, the length doesn't change. So let's make that something, let's make that formal, write it formally. So if Q has orthonormal columns, meaning Q satisfies Q transpose Q equals the identity. And I'm not requiring here that Q be a square matrix. It leaves lengths unchanged. So what does that mean? It means that the length of X is the length of QX for any X. And by any X, I mean any X that we can actually take to multiply, right? The sizes need to match. How to prove this thing? So the way to show it is, let's look at QX transpose times QX. What is this? This is simply the norm squared. Right? It's just easier to look at the square. If the square of the norms, so if I have this expression with the squares, I have the same conclusion, then I can make it without the square. So it doesn't matter what we prove here, whether we prove the norm squared or we prove just the norm, it's the same thing. So let's apply this transpose. What we get is X transpose Q times X, right? We have this equality. And since Q transpose Q is the identity, this is just the identity matrix, right? What we get is that this is X transpose X, which is the norm of X squared. So that is the proof that when you apply a transformation to a vector that is actually an orthogonal matrix, or the columns are orthonormal, you preserve lengths. Okay, why is that important? Why is it important that the lengths are being preserved? Well, that gives us actually numerical stability. So when we apply these matrices onto vectors, we know that the vectors, that the numbers inside the vectors or the components won't get too large or too small. We actually preserve, it gives us computational stability. All right, more on this in the next video.